hope. So this is a very challenging problem. I started working after I have wrapped up some of the work with Professor Robert Noah, and which is try to predict earthquake waveforms using generative AI. So why is predicting earthquake waveforms important? So there's a recent earthquake in Taiwan where like people are like kind of rage or like unhappy about how the weather bureau didn't send out the prediction of the size of the earthquake in real time that upset them. And also there's earthquake source parameter determinations, which requires a sufficient coverage of the azimuthal stations that to give a proper source moment tensor solution. So these two kind of problems in our daily life impose like predicting waveforms is kind of important, but how do we do this? So to start with the problem, there's actually from my start of the work, I dive deeply or straightforward into a waveform dataset that is recently published that have a lot of waveforms. And they also have around 11,000 events that have the moment tensor solution accompanied with. And the data set is a global data set. So at first we thought, okay, we have a large data set and we have a lot of waveform, but with the limited label of moment tensor, how should we construct a training data set to try to figure out how to predict waveforms with source parameters? And this is what a waveform actor reconstruction with multiple waveforms in a single event in a regional area looks like. As you can see, there are many like missing traces. So real data with a certain criteria when you want to construct a training data sets, there are always missing data, or at least in real world, there are always data that are missing. So in such case, we take a step back and try to see, okay, if we can try to fill up those missing waveforms in order to help us learning how to accompany the moment tensors and the waveform data. So we utilize something called image inpainting technique. So this is a means data set that has handwritten digits. And then so I first try to I take out the horizontal rows that is similar to what we have in our real data sets and try to employ a very simple neural network to see how it can fill in up the missing traces. So we just take out the horizontal as in our real training data. So you can see that it kind of does a little bit of work, but not actually being great on it. So we then introduce the network I'm using to verify whether we can go into this direction to solve the prediction of the waveforms by generative AI. So this is called a generative adversarial network. The way it works is it will have a training data set, and then you have a discriminator and a generator. What the generator does is it will generate a fake image or a fake data with a random noise. And then there will be a discriminator that will help to discriminate between the real data and then the fake data. And then as the two neural nets competing with each other, they will reach a stable state that they can kind of discriminate the real and fake and also generate something that is close to the real. And it sounds very maybe it's possible, but actually it is not. So as part have been introduced before, so we use the convolutional neural network layers to help us how to identify the pattern in the image. Because there are too many missing rows in our real data set, so our real data set actually failed because we have a limited size of data, and then the neural net couldn't identify the pattern. So I figured, okay, then I'll have to construct a synthetic data set to test whether it's the data's problem or is it because there are too many missing traces. So in real data, the missing traces can ranges from 30% missing to up to 70% missing, depending on the earthquake you are choosing and the station you are constraining. So I construct a synthetic data set with a fixed strike. So what does fixed strike mean? That means I have two waveforms which have positive polarity and negative polarity, and then I layer out them in a figure with a 0 to 360 azimuth. And then I construct a multiple of them and then try to fit into the neural net that is the same as in the MINS data set I was working on. And then try to take out random rows like in the real data set and to figure out like how many percentage loss in the traces I can tolerate to recover the pattern by the neural network. So the result is shows as here. So I have like 1 takeout rows, 2, 5, 8, and 10. And I have total of 32 rows after I compress the image for efficiency. So you can see that for 1, 2, and 5, you cannot fill the missing rows rather in a correct polarity and similar size of amplitude. But as the missing rows increases, the prediction of the missing rows becomes probably. So in this test, we figure out, okay, so for in real data, because there are so many missing data rows or traces, it's very impossible for the neural net to learn that on a 30% or more missing to capture the whole pattern of an image or the event. So one image represents an event with fixed stations around a region. And I also test on varying strike value. So if I change the strike value, the actual performance is not bad. It's not good because there are rotating patterns. And then because I use unsupervised learning, for this kind of problem, it might be better to use supervised learning with the generative AI. And if you look at the loss function, like the loss during the training, the neural network couldn't like reduce the loss in a varying strike value. So varying strike value means I will change the starting of the black and the rotation pattern from 0 to 90 degrees, and I create a larger like synthetic data set and try to see if it can capture the pattern. So there's even more problem when we look at the real data. So we might thought that the neural net might be do well or added something on the real data set if we construct and form patterns and have it to learn through it. But it actually says that for different earthquakes, you might not see a consistent pattern only with human eyes to identify the localized feature that can be learned by the deep convolutional layers. So in such case, there are data with good quality, like there might be a feature to be learned, or there are data that make complete no sense, and it's very hard for convolutional layers to scan through it and then capture the localized features. So to wrap up, so the overall loss will increase if we have more missing stations. And the fixed strike should do well, otherwise it would be like too impossible. But the various strike parameters, we have to do something different to get a better results.